Part 3. The Planets. The solar system is our planetary system. It consists of the Sun and the objects that orbit it, 8 planets, 2 dwarf planets, and numerous asteroids, comets, Kuiper belt objects, and gas, dust, and debris. The Sun itself accounts for approximately 99.86% of the mass in the solar system, yet the remaining 0.14% still adds up to approximately 2.8 times 10 to the 24th power kilograms of material, from which to make everything else in the solar system. All planets and most other objects in the solar system orbit at or very near the elliptic plane in line with the Sun's equator. The angular deviance of an orbit from that plane is called an object's orbital inclination. The definition of a planet is an astronomical body orbiting a star or stellar remnant that 1. Is massive enough to be rounded by its own gravity, 2. Is not massive enough to cause thermonuclear fusion, and 3. Has cleared its orbital path. Requirement 1 means that small, irregularly shaped objects, such as asteroids, cannot be planets. Requirement 2 rules out stars, even those that orbit other stars. Requirement 3, added by the International Astronomical Union, IAU, in 2006, means that objects like Pluto and Ceres, which meet the other 2 requirements, are not planets. This decision was made in light of the discovery of many objects in the outer solar system that fit the first 2 requirements. In addition, there appeared to be no reason not to call Ceres a planet under earlier definitions. Instead of changing the order of the planets by adding Ceres, the largest object in the asteroid belt between Mars and Jupiter, while also adding potentially many more outer system objects, the decision was made to classify Ceres and Pluto as dwarf planets. The terrestrial planets are the inner, rocky worlds of the solar system. These are, in order from the Sun, Mercury, Venus, Earth, and Mars. These planets are primarily composed of refractory materials, like silicate rocks in a crust and mantle surrounding a metallic core, mostly iron and nickel. They have a solid planetary surface that has been shaped by comet and asteroid impacts and tectonic forces, though only on Earth have plate tectonics been observed. 3 of the 4 terrestrial planets have atmospheres substantial enough to have weather: Venus, Earth, and Mars, while Mercury only has a tenuous atmosphere. The closest planet to the Sun, 0.4 AU, Mercury, is also the smallest planet in the solar system, at 0.055 Earth mass. 1 m equals 1 Earth mass. Mercury has no natural satellites. Its surface is marked by impact craters and wrinkled ridges called roops. Mercury's atmosphere is very tenuous, consisting mostly of atoms scoured from its surface by the solar wind. It does not, as might be thought, have the hottest surface of the planets, as its lack of atmosphere means that it does not retain heat, leading to its night side being cold. Venus, the second planet from the Sun, 0.7 AU, has been called the Earth's twin. At 0.815 Earth mass, it is the closest in size to the Earth. Like the Earth, it has evidence of internal geological activity, though not plate tectonics, and a thick atmosphere. However, Venus's atmosphere is about 90 times denser than Earth's, consisting of more than 96% carbon dioxide. This means that the surface atmospheric pressure on Venus is about 92 times that of Earth, like being 900 meters underwater on Earth. Carbon dioxide is a greenhouse gas, meaning it readily traps heat. Venus's thick atmosphere also has opaque clouds of sulfuric acid droplets. This and Venus's close position to the Sun mean that Venus is very hot. The mean surface temperature of 735 kelvins, 462 degrees Celsius, is hot enough to melt lead. Venus is also very dry. Any surface water it might have had has long since been driven off, leaving the surface a desert. Venus is the only planet to rotate around its axis clockwise in a retrograde rotation, when viewed from the perspective above Earth's North Pole. It also rotates very slowly, completing one rotation every 243 Earth days, shorter than the Venusian year of 224.7 Earth days. The Earth, our home planet, is the third planet from the Sun. It is the largest and densest of the terrestrial planets. It has one natural satellite, the Moon, which is the largest satellite with respect to its parent planet in the solar system, at almost 1/3 the diameter of the Earth. The current theory of the Moon's formation is the giant impact hypothesis, in which a large terrestrial planetesimal called Theia impacted the early Earth. The heavier elements merged with the Earth, sinking into its core, while the lighter elements formed a ring which quickly coalesced into the Moon. Earth is the only place where life is known to exist. It is unique in the solar system in having a liquid hydrosphere, with free liquid water always present. 71% of Earth's surface is covered in liquid water in the form of oceans, lakes, and rivers. This water is thought to be the result of comet impacts in the early solar system. Earth is the only terrestrial planet with current surface geological activity. Earth's solid inner core of iron and nickel is surrounded by a liquid outer core, a convective mantle and crust of largely silicate minerals. Convection in the mantle drives plate tectonics in the Earth's lithosphere, the upper crust of solid rock. This motion continually recycles crust material down into the mantle while producing new crust, meaning much of the Earth's surface is relatively young compared to the age of the Earth. The motion of the liquid outer core generates Earth's strong magnetic field, which in turn shields the Earth's surface from energetic solar radiation and the particles of the solar wind. Earth's atmosphere is unique in the solar system for the amount of oxygen, a result of life processes over billions of years. The atmosphere consists of approximately 78% nitrogen, 21% oxygen, approximately 1% water vapor, and approximately 1% argon, with the remaining atmosphere consisting of trace amounts of carbon dioxide, methane, and noble gases such as neon and helium. This atmosphere drives weather, which is an important force in continually shaping the Earth's surface through erosion. The atmosphere is important in protecting life from solar radiation. The ozone layer in the upper atmosphere absorbs incoming solar UV radiation that would otherwise be harmful to life on the Earth's surface. Mars, the fourth planet from the Sun, 1.5 AU, is smaller than the Earth and Venus at 0.107 Earth mass. Mars has a carbon dioxide atmosphere at roughly 0.6% Earth's atmospheric pressure. Mars is covered with volcanoes, including the largest mountain in the solar system, the vast shield volcano, Olympus Mons. The volcanoes and other features, such as huge rift valleys, show that Mars was once geologically active. However, there is no current evidence of ongoing geological activity. There is evidence from surface features and minerals that Mars once had surface liquid water, but currently all water on Mars appears to be frozen in its polar ice caps or underground. The surface of Mars is red from large amounts of iron oxide in its soil. Mars has two tiny natural satellites, Phobos and Deimos. They are thought to be asteroids captured from the asteroid belt. Between the orbits of Mars and Jupiter, 2.2 to 3.2 AU, separating the terrestrial inner planets of the solar system from the gaseous outer planets, lies the asteroid belt. Orbital resonances with Jupiter, where the orbital periods fall into fixed integer ratios, making portions of the asteroid belt region either stable, resulting in clumps of asteroids, the 3-2, 4-3, and 1-1 resonances, or unstable, ejecting masses that fall in those regions, the 4-1, 3-1, 5-2, 7-3, and 2-1 resonances. These orbital resonances make it hard for planet-sized bodies to form gravitationally and also make the orbits of large bodies in the asteroid belt unstable in the long run. Objects in the asteroid belt range in size from tiny grains to the dwarf planet Ceres, 2.77 AU, 0.00015 Earth mass. The composition of these asteroids falls into three main groups: carbonaceous, C-type, silicate, S-type, and metal-rich, M-type. The total mass of all objects in the asteroid belt is small, only approximately 4% of the mass of the Moon. More than half the mass of the asteroid belt is contained in the four largest objects: Ceres, Vesta, Pallas, and Hygeia. There are over 200 asteroids known to be over 100 kilometers in diameter, and between 1.1 million and 1.7 million asteroids with a diameter of 1 kilometer or more. This mass is distributed over a vast area of space, meaning the asteroid belt is very diffuse. Located in the outer solar system, beyond the asteroid belt, are the giant planets, also known as the Jovian planets, after Jove, another name for the god Jupiter. These planets in order of distance from the Sun are Jupiter, Saturn, Uranus, and Neptune. These are massive planets composed primarily of volatile materials such as gases and ices, rather than the rocky material of the terrestrial planets. Jupiter and Saturn are sometimes grouped together by composition as the gas giants, while Uranus and Neptune are grouped as the ice giants. The giant planets are thought to have small solid cores. The composition of these cores is unknown, but is theorized to be molten, with a rocky composition, possibly surrounded by gases compressed by the vast pressure into metallic form. Jupiter, the fifth planet from the Sun, 5.2 AU, is 2.5 times the mass of all the other planets put together, at 318 Earth masses. It is composed primarily of hydrogen and helium, with an outer atmosphere that is segregated into distinct bands at different latitudes, with turbulence and storms along their boundaries. Prominent among these storms is the Great Red Spot. Jupiter has an intense magnetic field, hinting at its internal motion. Jupiter has 79 known natural satellites, including the four large Galilean moons, Io, Europa, Ganymede, and Callisto. Europa is believed to have a liquid water ocean under its outer crust of ice, making it a target for exploration as a possible location for extraterrestrial life. Jupiter also possesses a faint ring. Io is the most volcanic spot in the solar system, with a surface continually reshaped by volcanic activity. This volcanic activity is thought to be due to the intense gravitational forces acting on Io from Jupiter and the other Galilean moons, which knead and heat the interior of Io. Jupiter has captured many asteroids, both as moons and at its L4 and L5 solar Lagrange points, preceding and following it in its orbit, known as Trojan asteroids. They are named after characters from the Iliad, with the preceding group known as the Greek camp and the following group as the Trojan camp. Saturn, the sixth planet from the Sun, 9.6 AU, is distinguished by its extensive ring. Saturn has 60% the volume of Jupiter, but is less than a third the mass, at 95 Earth masses. Saturn is the least dense planet in the solar system and is less dense than water. Its composition is much like Jupiter's, primarily hydrogen and helium. Saturn has 62 known natural satellites, moons, the largest of which are the rocky Titan and Rhea. Saturn's other moons are mostly ice. Titan is the second largest moon in the solar system, larger than the planet Mercury, and the only satellite in the solar system with a substantial atmosphere. Saturn's planetary rings, sheets of particles orbiting the planet, are primarily composed of water ice. The rings extend outward 6,630 to 120,700 kilometers from Saturn in distinct bands, but are only on average 20 meters thick. Uranus, the seventh planet from the Sun, 19.2 AU, is also the lightest outer planet at 14.5 Earth masses. Uranus, along with Neptune, is an ice giant, composed primarily of methane, ammonia, and water ices, with traces of other hydrocarbons, in contrast with the hydrogen and helium of Jupiter and Saturn. Uranus has the solar system's coldest atmosphere, with a minimum temperature of 49 kelvins, -224 degrees Celsius. Like the other giant planets of the outer solar system, Uranus has a ring system, a magnetosphere, and numerous moons, 27 known. Uranus is unique in having an extreme axial tilt, over 90 degrees from the ecliptic. It is theorized that Uranus was struck by a large impactor sometime in the past, causing the unusual tilt. The outermost planet, eighth from the Sun, 30.1 AU, is Neptune. Though Neptune is slightly smaller than Uranus, the other ice giant, it is more massive, 17 Earth masses. It also radiates more internal heat, making its atmosphere warmer than Uranus despite being farther from the Sun. Neptune has 14 known satellites, the largest of which, Triton, is geologically active, with geysers of liquid nitrogen. Neptune is also accompanied by several minor planets, the Neptune Trojans, in 1-to-1 orbital resonance with it. Outside the orbit of Neptune, the trans-Neptunian region, lies a donut-shaped area known as the Kuiper Belt. This ring of debris is similar to the asteroid belt, but much larger in volume, extending from approximately 30 to approximately 50 AU. Kuiper Belt objects, KBOs, are composed mostly of ices of water, methane, and ammonia. They include anything from dozens to thousands of dwarf planets, including Pluto, the largest KBO, Makemake, and Haumea, as well as other named objects, including Sedna, Quaoar, Varuna, Orcus, and Eris. The Kuiper Belt itself was once thought to be the source of short-period comets, but it is now believed that the scattered disk, a region that overlaps the Kuiper Belt and extends much farther out, is the source of these comets. The Oort cloud is a theorized region of up to 1 trillion icy objects surrounding the solar system out to 50,000 AU, or even as far as 100,000 AU. It is thought to be the source of all long-period comets that visit the solar system. This region remains almost entirely unmapped. One hypothesis is the nebular hypothesis. The solar system formed from a collapsing molecular cloud of interstellar gas and dust, a pre-solar nebula. Conservation of angular momentum caused the pre-solar nebula to rotate faster and flatten into a protoplanetary disk of diameter approximately 200 AU. A hot, dense protostar formed at the center of the disk. Planets formed from gas and dust in the disk, attracting each other via gravitation, a process called accretion. The process of differentiation also contributed to the formation of the planets. Due to their higher boiling points, only metals and silicates could exist in the inner solar system near the Sun, forming the rocky terrestrial planets and asteroids. There was only a small amount of these materials in the pre-solar nebula, so the terrestrial planets didn't grow as large as the outer planets. The outer giant planets formed beyond the frost line, where gas and volatiles, such as ices, could form. There was more of this material, so the giant planets could grow to be giants. After approximately 50 million years, the pressure and density of hydrogen at the center of the protostar was enough to ignite thermonuclear fusion. The temperature, pressure, and density increased until the outward thermal pressure balanced the force of gravity, at which point hydrostatic equilibrium was achieved. The solar wind, the flux of particles from the Sun, swept away all the remaining gas and dust from the protoplanetary disk into interstellar space, ending planetary formation. Extrasolar planets, or exoplanets, are planets outside of our solar system circling stars other than our Sun. Exoplanets are hard to detect as they are cool, much smaller than their parent stars, and orbit in ways that are hard to predict from Earth observation. Exoplanet searches that rely in imagining are usually in the IR spectrum, as they are heated by their star, unlike stars that emit all wavelengths. It is not usually feasible with current instruments. The transit method requires specific geometry to carry the exoplanet between the star and Earth. Microlensing also requires specific geometry. The Doppler wobble method detects movement in the parent star by red-blue shift of the spectrum. It is harder to detect smaller, farther-out planets. Therefore, many of the exoplanets we have been able to detect are larger and/or close to their parent stars. Hot Jupiters must have formed farther out past the frost point and then migrated closer to their stars. Life is theorized to require liquid water. Exoplanets that could have liquid water are said to be in their parent star's circumstellar habitable zone, CHZ, or Goldilocks zone, since they are not too hot, not too cold, but just right. This is the end of Part 3, the planets. In the next video, we'll cover the Sun, stars, and galaxies.